I'm Rakesh. I work at Lyft. I'm here to present on scaling real-time feature generation platform, like how we scale the real-time feature generation platform at Lyft. And before that, what are the things that I'm going to cover in this talk? Mostly around the context around what is the ecosystem, then data consistency and accuracy requirement, feature serving evaluation or not evaluation, evolution of pipeline, like how they evolve at Lyft, and then performance optimization that we did over them to get a kind of better performance and also to perform the pipeline or scale the pipeline for different use cases. And then I'll also talk briefly about the data lineage and traceability requirements, why those things are needed, and then at the very end, strategies for pipeline design that we used. For the context, for those who do not know about Lyft, Lyft is a leading ride-sharing company that facilitates millions of rides across hundreds of cities. The company is leveraging sophisticated data processing and machine learning infrastructure to optimize operations and ensure scalable efficiency across all the current cities. To further provide the context, we use data processing and ML in different use cases. I have listed down a couple of use cases over here, but there are many more there. One of them is the dynamic pricing. We dynamically adjust the prices to control the demand and supply. And this is mainly to prevent the catastrophic failure of the platform. To give you some examples, right? Like if you do not have a dynamic pricing in place, and there is a high demand, and almost everyone is requesting for a ride, and we match all of them and try to match all the driver, then there will be no driver at the next minute. And those people who come later and try to book a ride, they will not find drivers, and they have to wait a really long time. And it is a catastrophic failure, mainly because riders are not able to find the ride, and later on, once those drivers who dropped off the passenger and come back on the platform, they will not find the ride. So it's kind of a lose-lose for both of us, for the platform as well as for the drivers as well. And that's why we have a kind of a dynamic pricing, which is dynamically adjusting the prices based on the current marketplace scenarios, right? And it is the data processing is really important over here because we are monitoring the demand and supply in almost real time, and that information we feed it into the machine learning model, which determines the right level of pricing to have a kind of better throughput of the system or the platform. And then we also have a demand forecasting. Demand forecasting is also important because we want to know when will be the demand and how we can reserve our supply or even position our supply to different places to satisfy those demand. And there is another key factor that we also take into consideration about the ETA, time for pickup of the passenger, right? Or even a drop off. So those ETAs are really important. And so that's why our platform is always getting all these data in real time, trying to process it and trying to determine what will be the sweet spot when we can position our different drivers in different locations and try to reduce the pickup ETA. And then the matching and routing, that also goes hand in hand. Matching is basically for all the different ride requests, we want to match with the drivers, right? We cannot just match any driver or whatever the drivers are available on the platform. We have to determine what will be the pickup ETA, whether that ETA is good or not, whether if the driver is too far away from that place, and if he has to drive too long to pick up, that is not good. Even though we will be able to satisfy the demand, but it is not good, mainly because we do not pay the driver for the pickup. We pay very marginally for those kind of, they are mainly get paid when they are serving for a ride, like when they are dropping off the passengers. And similarly, routing as well, we need to determine what is the shortest route, what is a route which has the kind of smallest ETA. So that way, the driver can reach to the passenger, as well as they can go and drop off those passengers as well. And then the other one is like our platform is wide, and then there are different actors interacting with the platform, and definitely there are bad actors as well who wants to leverage the platform, and they want to commit a fraud and all those things. So our platform is basically processing all these data points and trying to detect all these fraudulent activity and trying to prevent them in time. Similarly, we also have some safety features. What we do is we are trying to gather all these data points in real time, trying to detect if there is any kind of safety concern, and if there is any kind of safety concern, then try to put the right measures in place to prevent any kind of bad experience, either for driver or passenger. And then there are other use cases. I'm not going to go over all the use cases for now. And then let's dive into the what is a DSA, like data science and ML workflow looks like at Lyft. So generally what happens is like, product manager will come and try to solve one problem, right? Like I listed a couple of them in the previous slide. So let's say for the new problem, they come and they say, okay, we want to solve this problem. They generally discuss it, how we are going to solve this problem. And then what happens is like, data science or ML engineer, they will come up with a theoretical model that they can, that model can solve that issue, right? And generally what happens is like that, after that, once they have a theoretical model, they try to figure out what are the features that they need. The feature could be stored in kind of offline data base, or, and these features could be already processed, or it could be also based on some kind of raw data points, right? If we take an extreme example where we are building a model, where we are building a brand new model, and all these features are not existing, and they have to, they have to look into all these raw data points and try to process it. So in that case, in that case, what happens is like that we create a kind of, or data scientists, they create a kind of SQL queries to basically transform the data into a feature, and then they use that feature in their model. And generally, they use PyNotebook environments to basically, consume those features, evaluate that model. And if that model is looking promising, then we go forward with like kind of productionizing it. But in productionizing, there are like different steps involved as well. One is like, we cannot go directly and put it into production. We have to do in a kind of a shadow mode as well. So when we do in a shadow mode, basically we are directing some of the traffic to a kind of shadow, or we are shadowing some of the traffic and just sending it to the newer model. And then we evaluate how the model is performing. If the model is performing better, then what we do is like we go to the next step, which is called A/B testing. One thing to note that like some people will say that, okay, if we're already shadowing the model, why we have to go through the A/B testing? I think there is a problem, like when you shadow traffic, what if the model is performing right and the data it is generating? It is very isolated, like it does not have any effect on the ecosystem. But when you put in the production, there are like, when the model is making a decision, it is also going to downstream services and it's affecting the overall ecosystem. So it is necessary to basically put in the kind of experimentation phase, and in production, that's when you see the real effect of the model. And we do it as part of the, what you call A/B testing. And once we have successfully run the A/B testing for 1 month or so, and if the results are looking great, then we do a full production rollout. One thing which I also forgot to mention, that when we are converting these offline queries into a kind of online feature or pipeline which are generating these features, we also have a kind of a data validation in place. Just to make sure that like when we are generating all these data, these are accurate and they do not diverge over time. And it is very important because we have seen in past where data degrade and then the model also degrade. And if we do not have such kind of a system in place or observability in place, then it's hard to detect the degradation, and which is also very costly for the business. I think I already covered that one, but whenever we convert the SQL, the offline SQL query into the pipeline, we generally have this step of like data validation in place just to ensure that everything is accurate. And most of the conversion, they have a really good, high quality feature. And in most of the case, the MAPE, we use the MAPE to evaluate the accuracy of the feature, and most of the time it is less than 0.005%, which is quite good. Some people will argue that like why we do not have 100%. I think it's by the nature, like in the offline table, you have all the data present, and you can just run the query, you can get the data. But in real world or in a real-time pipeline, it's kind of hard because some of the data could be delayed, and we cannot just wait forever for those delayed data. And in that case, like we just move forward to process the data and provide the feature to the downstream. And that's why you see a kind of some error in the data. And I think in our use case, it is perfectly fine. Most of our use cases are based on the latest data that we want to consider, and it is important mainly for when we are making all this decision to balance out the marketplace systems. So it's fine, but if it is some kind of financial system, then it's really important to have all these highly accurate, like 100%, right? But in our case, it is not required. Okay, another one is feature serving. So in this ecosystem, we also have feature serving in place, and they are divided into different dimensions. One is like synchronous versus asynchronous feature serving. For synchronous feature serving is basically based on the services. You call the service, you get the feature, and that's how you use it. These things are mainly used for synchronous inferences. For example, let's say for a given session, we want to figure out whether this session is fraudulent or not. And in that case, like we cannot just wait for several seconds to figure out. Like at least in some of the cases, we try to run the inferences in that particular session, try to determine it if it is fraudulent or not. If it is not, then move forward. Otherwise, like you can block that one. So for those kind of cases, like we use service-based feature serving, whereas the asynchronous feature serving is also used in those cases where you can run these interference in kind of asynchronous mode, determine those values, store in a service, and then that can be used for serving later. For example, the prime time or surge prices, you can compute that one in an asynchronous space, mainly because you are doing a kind of aggregation for demand and supply, trying to figure out how the right prices, and those things can be done in asynchronously as well. And then that value is stored in a service, which they later on fetched by the other service, or even the the mobile clients as well. Then in our ecosystem, we also have a point feature versus geospatial aggregated feature. Point feature is basically a kind of a feature which is related with one entity. This entity could be a session, this could be a driver or passenger related information, whereas the geospatial aggregated features are the one which are aggregated over different sessions. For example, for prime time, we consider what are the demand, or like what is the demand in particular geohash or in a city, and similarly for for supply as well. So those kind of things are already aggregated and stored, and they are generally aggregated. And there are some use cases, mainly for those use cases where you want to optimize for across multiple sessions or a geographical location. That's when we use all these aggregated features. So, and let's move on to the evolution of pipeline. So I think we started using Beam almost, I think starting in 2018 or something. And I think we are the we are the first company who kind of productionized the cross-language pipeline as well. Our pipelines are written in Python, and then we are running on Apache Flink. And when we first introduced it, since we had less experience building the pipeline, we tried to do everything in one pipeline, like even the feature generation, modelization, everything. At that time, it did not scale well. At that time, we ran into multiple problems. One is the memory leak when we were running all these models. These were using some heavy lifting libraries. They did not scale well in the production. The other part was like when we tried to tune these pipelines for performance, they did not work, mainly because the feature generation pipeline is ingesting millions or hundreds of millions of data points every minute or so, and they are processing, and they are doing heavy lifting, all of them, and then reducing that data to almost tens of millions of data points, and then passing into the model DAG. So that did not perform well. And then we realized that, okay, there are two different performance characteristics that we are trying to optimize here in one pipeline, which is really hard to achieve. Then what we did is like we tried to break it down into two pipelines. One primarily focusing on the feature generation. The other one is mainly for orchestrating the model DAG and computing all these decision variables and then passing down to the downstream services. And I think in the initial version, it was just for one use case that we had launched, and it was okay at that point to generate all these features, and it is a kind of, and then directly consume it in the model inference, and it was a kind of a closed system. But over time, what we realized is that, okay, the same feature can be used by different models, different products, right? So we need to have some kind of a feature sharing as well. And that's why like we divided this into two pipelines, and it made sense after that. And the other one is like, since they are two separate pipelines, so it's much easier for us to scale individual pipelines. And since they had a kind of different characteristic, we had to use different configuration that worked fine for them. And it worked fine. Great, like from one use case to almost 10 or 20 use cases, like we were able to achieve by this pipeline. But then we realized that even this one is not doing the justice. Like we realized when we created multiple pipelines that the initial section of the pipeline, which is doing the filtration, data compaction part of it, and then aggregation. So the very first two stages were almost similar for those pipelines, and we realized that we are kind of wasting our resources doing all these jobs, like repeating or kind of duplicating this logic in multiple pipelines. So what we should be ideally doing is further dividing that feature generation pipeline into multiple sections, and that can give us more advantage. So what we did is we further divided that feature generation pipeline into two sections, one for mainly for data like ingestion and enrichment pipeline, and then the other part was the aggregation pipeline, which mainly aggregates that data. So in the data ingestion pipeline, what we do is like, there's one more benefit that we realized once we did that, is that in the initial version of the pipeline, it was mainly focused for one use case or one or two use cases. And over time, we realized that you want to provide the state of the user, right? Like the driver state or passenger state. What is their current state? And in earlier pipeline, it was not. It was just a kind of very based on one particular event, not a kind of history of that driver or passenger. Over here, over time, what we did is like we build more complicated feature. And to build those more complicated feature, you need to know the history of that entity. It could be driver or passenger. And in this case, what we did is like we kind of stored all the relevant information in the state, Flink state, and we emitted all these data regularly. It's more kind of a snapshot. And we also tag this data with different tags. So that way, like if some user is interested in particular event or a series of event, they can use that data, like they can filter the data based on that, and they have a full history of that particular entity. That way, they were able to build more complicated feature. For example, like let's say we want to know a driver, like how long this driver has been waiting, whether did this driver get any kind of ride in last 5 minutes or not. So all these things were baked into this one, and it was much easier for us. Since we had optimized this pipeline, and this pipeline is shared across different aggregated one, so that way, like, we were able to save the computation cost as well. Cool. And the other thing, like, once we defined that pipeline, we had multiple pipelines. Data processing is only one pipeline, the initial data processing one, and then you have multiple. We saved it. What was the next problem that we ran into? So as I had mentioned earlier, like, we have to convert the offline query into the online query, and then you have to involve all the engineers, and then they would develop all these complicated features, right? And we wanted to remove that engineering from this process, but the only problem is, like, if you do that, then you have to train all these data scientists about this pipeline, how they behave it, and all those things. And what we realized that if we convert more kind of a configuration-based pipeline, then it's much easier for them to build all these pipelines. And we introduced the YAML-based pipeline. Some people might be wondering, like, why this syntax is looking different. It is more our proprietary way of, like, defining a YAML-based pipeline. I think we initially introduced it, and since then we have been continuing with that one. And by introducing this YAML-based pipeline, that also provided a way, like, where anyone can define the pipeline. So we do not have to introduce an engineer to create the pipeline and run the pipeline. That simplified a lot of processes. Then performance optimization of these pipelines. So one thing that while, like, building the entire process or building different pipelines, we realized that when we initially built all this pipeline without understanding the data, we had to go through several iterations to tune the pipeline and all those things. And then what we did is, like, we said, no, like, we need to understand the data very beginning when we are designing this feature or pipeline. That made us kind of a lot of improvements in the sense that, like, we would add all these optimization early on during the development and not going through different iteration of pipeline improvements. Then another thing that we realized that we were getting tons and tons of data, and from that data, like, not necessarily all the data will be used for the feature generation. We had to drop almost 70 to 80% of the data. Like, in two forms. One is, like, sometime there are noisy events that are generated by the upstream services, and not all the data is used. So we have to aggressively drop all the data. The other part was in terms of, like, all these data points will have different attributes. Like, they will have hundreds of attributes. We may not be using all these hundreds of attributes in our computation. And what we did is, like, we just filter out all those attributes which are necessary for the feature, and we just drop all of them. And when we had applied that one, this filtration logic, though it was very simple, we had seen at least 20 to 30% improvement in computation. And then the other one is, like, when we initially designed the pipeline, we noticed that the data processing, we had to distribute the data processing across. Like, as a kind of a service-oriented, or like those engineers who were used to write all these service, they used to think that you can write in one function, one file, you can process everything. That does not work for the pipeline. You have to be really mindful when you're processing data. You have to vertically or horizontally distribute the data across different operators. The other one is, like, avoid mega pipelines. Like, we tried to build a kind of bigger pipeline initially that did not scale well. And we realized that you have to be mindful, like, how, what are the things that a pipeline will be doing, and try to avoid those things. you do not want to go on either extreme. You do not want to go on one extreme where like you are doing too many things, or you do not want to go on the one extreme where you are doing a little thing in a pipeline. If you do less thing in the pipeline, then probably you will be introducing kind of more latency, end-to-end latency that you want to avoid. And another one is partition and data strategically. It is really important that you partition the data. Like if you do too much partition, there is possibility that some of the partition they are not doing much, and some of the other partition they are doing too much. So as you dive deeper into data and try to figure out what is the right partitioning, then it makes sense to adjust your partitioning and then process it accordingly. And then the other one is state management. As I said earlier, we moved to a state processing where we were storing all the data points and trying to understand what is a state or what is the history of that entity. And we used to store all the data, but we realized that you do not want to store for too long because that will increase the overall data size and that will also slow you down. So you have to determine what is the right time when you want to push the data. And then, and the other one is partition source smartly. Initially, we thought we can partition as many as we want, but we ran into some kind of weird issue as well. Like some of the partition did not get enough data, and then those partition had a kind of idle. And one specific scenario where if the partition is idle, somehow the Flink was not able to process it further. And we had to put some logic there to, especially for those idle partition, to process further. Even though there is no data, then you just move further. And then the other part is the data lineage and traceability. I think it's very important in the ecosystem when someone is generating data and someone else is consuming it and transforming into a feature, and then downstream you are using it for model inference. And if you do not have a kind of a good visibility, then it's kind of bad. We ran into situations where the upstream data producer, they change attributes without knowing that these attributes are used downstream. And in certain cases, they change the value as well. And that affected the feature as well as the downstream model performance. Since we had our own validity or validation, feature validation in place, we were able to catch all these problems. And we were able to identify the source. But it took some time to identify the source. If we have a kind of better visibility in place, then you will be able to quickly identify the team and notify the problem. Yeah. And that's why we build another kind of traceability framework in our ecosystem to quickly identify the source and notify them.